Look up at the night sky right now, wherever you are. What you're seeing is just the beginning of an answer to one of humanity's most profound questions. How many stars actually exist? Not a vague guess or a poetic metaphor, but a real number based on careful observation and rigorous calculation. By the time we finish this journey together, you'll understand not just the answer, but why it matters and how we discovered it. Before we venture into the cosmos, if you enjoy explorations like this, a quick like or subscribe genuinely helps the channel grow and reach others who share your curiosity. It's simple for you, but it makes a real difference here. Now let's begin. Think about counting for a moment. It's something you learned as a child, something so fundamental you barely think about it anymore. 1, 2, 3, 4, simple enough. You can count the fingers on your hand, you can count the people in a room. But when does counting become impossible? When do numbers become so large that they transcend our ability to comprehend them? Most people can accurately estimate quantities up to about 7 or 8 objects at a glance. This is called subitizing, the ability to instantly recognize small numbers without counting. Beyond that, we start estimating rather than truly perceiving. A crowd of 20 people versus 30 people? Most of us would struggle to tell the difference without counting methodically. 50 versus 70? Nearly impossible to distinguish. This limitation isn't a personal weakness, it's how human cognition developed over hundreds of thousands of years. Our ancestors needed to quickly assess immediate situations. How many predators approaching? How many people in my tribe? How many animals in that herd were hunting? These numbers rarely exceeded a few dozen. Natural selection never created mental tools for intuitively understanding millions or billions, because those quantities never mattered for survival. When someone mentions that a football stadium holds 80,000 spectators, you accept it intellectually. You process it as information. But you don't truly feel what 80,000 means the way you feel what 5 or 10 means. You can't picture 80,000 the way you can picture 5 apples arranged on a table. The number exists in your mind as an abstraction, not as a visceral reality. This creates a fundamental problem when we discuss stellar populations. The numbers involved are so fantastically large that they exist completely outside human intuition. They're not just big numbers, they're numbers that obliterate our natural sense of quantity. So before we can meaningfully answer how many stars exist, we need to build a framework for understanding large numbers. We need to develop genuine comprehension of scale. Let's start with something concrete. Imagine you decided to count to 1 million. You sit down, determined, and begin. 1, 2, 3. You count one number per second, never pausing, never sleeping, never eating. Just pure continuous counting. How long would this take? 1 million seconds equals approximately 11.57 days. Not quite 2 weeks of continuous counting. It's challenging, certainly. A test of endurance and focus, but it's conceivable. You can imagine dedicating roughly 12 days to such a task. People have run longer ultramarathons. People have stayed awake longer for various challenges. 1 million is large, but it's within the realm of human scale. Now let's jump to 1 billion. Same scenario, same dedication. You're counting one number per second continuously from the moment you're born. 1 billion seconds equals approximately 31.7 years. Think about that. You'd start counting as a newborn infant and finally reach 1 billion in your early 30s. Your entire childhood, your education, your early career, all would pass while you counted. Every birthday, every holiday, every significant life event would occur during this unbroken count. What seemed merely challenging with 1 million has become something that consumes a human lifetime. The difference between 1 million and 1 billion isn't just numerical, it's existential. It's the difference between a difficult task and an all-consuming lifelong commitment. Now let's consider 1 trillion. At one count per second, reaching 1 trillion requires approximately 31,088 years. You'd need to have started counting before humans developed agriculture, before we invented writing, before we built cities or organized into civilizations. You'd have been counting when our ancestors were nomadic hunter-gatherers navigating the Moe Ice Age. The entire span of recorded human history, all of civilization, would constitute just a fraction of your counting journey. Think about what this means. The pyramids were built while you counted. The Roman Empire rose and fell while you counted. The Renaissance occurred while you counted. The Industrial Revolution, the World Wars, the Space Age, the Internet, all happened while you methodically continued counting, and you still wouldn't be finished. The leap from million to billion is a multiplication by 1,000. The leap from billion to trillion is another multiplication by 1,000. These aren't just bigger numbers, they're fundamentally different categories of magnitude. Our brains process them as similar because they're all big numbers, but the actual differences are staggering. Here's what makes discussing stellar populations so challenging. When we talk about the number of stars in the universe, we're dealing with numbers that make a trillion seem almost quaint. We're talking about hundreds of billions of trillions. Numbers so incomprehensibly vast that even our trillion comparison fails to adequately convey their scale. But we're moving too quickly. Let's return to what we can actually observe. Let's start with what ancient humans could see, what you can see right now if you go outside on a clear, dark night far from city lights. On an exceptionally dark night, in a location with no light pollution, with your eyes fully adjusted to darkness, you can see approximately 2,000 to 5,000 individual stars with your naked eye. The exact number depends on your location, your eyesight, atmospheric conditions, and how patient you are in letting your eyes adapt. Let's call it roughly 4,000 stars for this discussion. 4,000 stars. That's the observable universe as far as humanity was concerned, for the first 99.9% of our existence. That's what ancient astronomers worked with when they mapped the heavens. That's what philosophers contemplated when they pondered the cosmos. 4,000 points of light scattered across the celestial sphere. Here's something remarkable. Every single one of those 4,000 visible stars belongs to our galaxy. Not one is from another galaxy. They're all part of the Milky Way. Moreover, they're all relatively nearby in cosmic terms. Most exist within just a few hundred light years of Earth. The farthest star you can see without a telescope is approximately 16,000 light years away. That sounds impressively distant until you learn that the Milky Way galaxy is about 100,000 light years across. When you look at the night sky with your naked eyes, you're not observing the universe. You're observing your immediate stellar neighborhood. You're seeing less than 1% of our galaxy's stellar population. It's like standing in New York City and claiming you can see all of North America. The Milky Way is classified as a barred spiral galaxy. Picture a disc-shaped structure with a dense, bar-shaped region through the center and graceful spiral arms curving outward from that central bar. Our Sun sits in one of those spiral arms, in a relatively sparse region about 26,000 light-years from the galactic center. That's approximately 153 quintillion miles, or if you prefer metric, about 246 quintillion kilometers from the dense core where stars are packed far more tightly than in our neighborhood. When you notice that faint milky band of light stretching across the sky on a truly dark night, that subtle glow that gave our galaxy its name, you're looking edge-on through the galactic disk. You're seeing the combined light of millions upon millions of stars, each too distant and dim to resolve individually, all blending together into a soft, luminous river across the heavens. Everything visible to your unaided eyes, every constellation you've learned, every bright star you can name, all of it exists within a relatively tiny bubble surrounding our solar system. You're seeing just the nearest neighbours in a vast galactic city. This is where telescopes revolutionised everything. When Galileo Galilei first turned a telescope toward the heavens in 1609, he made a discovery that fundamentally shook astronomical understanding. That Milky Band wasn't a cloud of glowing gas or cosmic mist as many had theorized. It was stars, individual stars, countless stars too faint for naked eye detection but perfectly clear through his relatively crude telescope. Each improvement in optical technology revealed more. Larger lenses and mirrors collected more light, exposing fainter objects. Better manufacturing techniques created clearer, sharper images. Longer exposure times allowed detection of extremely dim sources. The count of visible stars kept climbing. Thousands became tens of thousands. Tens of thousands became hundreds of thousands, eventually millions. So how many stars actually populate the Milky Way galaxy? This is a more complex question than it initially appears, and the complexity reveals something important about the challenges of counting cosmic objects. First, we can't see most of our own galaxy. Dense clouds of interstellar dust block our view in many directions. When you look toward the galactic centre, you're attempting to peer through thousands of light years of obscuring material. It's like trying to see through thick fog. Light from distant stars gets absorbed and scattered before reaching our telescopes. Entire regions of our galaxy remain hidden from optical observation. Second, most stars are extremely dim. Red dwarf stars, which constitute approximately 70 to 75% of all stars in the galaxy, are so faint that not a single one is visible to the naked eye despite being incredibly common. If you could suddenly see all the red dwarfs in our stellar neighbourhood, the night sky would be packed with thousands of stars where you currently see dozens. The cosmos would look radically different. Third, we're inside the thing we're trying to measure. Imagine standing in the centre of an enormous forest and trying to count every tree. You can count nearby trees fairly easily, but distant trees are hidden behind closer ones. The forest extends in all directions beyond what you can see. You're surrounded by the very thing you're attempting to census. This creates fundamental observational challenges. Astronomers have developed several clever techniques to work around these problems. They count stars in specific regions where visibility is good and extrapolate to the total galactic area. They measure the total mass of the galaxy, using gravitational effects on orbiting objects, and estimate what fraction of that mass consists of stars versus gas, dust, and dark matter. They study other spiral galaxies similar to ours that we can observe from outside, and use those as templates for understanding our own. All these methods contain uncertainties. Different techniques yield slightly different results, but they converge on a consistent range. The Milky Way contains between 100 billion and 400 billion stars, with most estimates clustering around 200 to 250 billion. Let's settle on 200 billion stars in our galaxy. If you counted them at one per second without pause, it would take over 6,300 years. You'd need to have started counting before the first Egyptian dynasty, before Stonehenge was constructed, before the earliest known writing, systems were invented. You'd still be counting today. Consider what this means for your perception of the night sky. You might see 4,000 stars on the darkest night, but they're floating in a sea of 200 billion. For every star visible to your eyes, there are approximately 50 million you cannot see. Your view of the night sky is sampling an infinitesimally small fraction of your galaxy's stellar population. You're seeing less than 0.02% of the total. This is our home galaxy. The gravitationally bound system of stars, gas, dust, and dark matter that contains our solar system, the structure we belong to. And it's just one galaxy among countless others scattered across space. The universe doesn't contain one galaxy. It contains galaxies by the trillions, each one a massive system of stars separated from others by vast reaches of mostly empty space. This is where the numbers transition from merely large to genuinely incomprehensible. Counting galaxies presents similar challenges to counting stars, but magnified to cosmic scales. We can observe galaxies in all directions scattered across the sky. But the deeper into space we look, the fainter and more difficult to detect they become. Small galaxies at great distances require enormous telescopes and extremely long exposure times to reveal. For most of the 20th century, astronomers estimated the observable universe contained approximately 100 to 200 billion galaxies. This estimate came from pioneering surveys like the Hubble Deep Field, where the Hubble Space Telescope pointed at a tiny, apparently empty patch of sky for many days, collecting every possible photon of light. That tiny region, covering an area of sky equivalent to looking at a tennis ball from 100 meters away, revealed about 3,000 galaxies in what had appeared to be empty darkness. By extrapolating that density across the entire celestial sphere, astronomers calculated the universe must contain roughly 100 to 200 billion galaxies. Then, in 2016, a study using new analysis techniques revised this number dramatically upward. By accounting for galaxies too small and faint for even our best telescopes to detect individually, researchers estimated the observable universe contains approximately 2 trillion galaxies. Not 200 billion. 2 trillion. 10 times more than previous estimates suggested. This revision didn't come from suddenly discovering new galaxies. It came from better understanding how many galaxies we're missing. We can detect large, luminous galaxies relatively easily. A massive spiral or elliptical galaxy stands out clearly even at great distances. But small dwarf galaxies, irregular galaxies, and distant galaxies whose light has been stretched and dimmed by cosmic expansion are incredibly difficult to observe individually. When we account statistically for all these faint galaxies we can't see directly, the total count increases dramatically. 2 trillion galaxies in the observable universe. That's our current best estimate based on the most sophisticated analysis techniques available. It's crucial to understand what observable universe means here. It doesn't mean everything that exists. It means everything we can possibly observe from Earth, given that light travels at a finite speed and the universe has a finite age. The universe is approximately 13.8 billion years old. Light from objects more than 13.8 billion light-years away hasn't had enough time to reach us yet. We cannot observe those regions not because they're too faint or our telescopes aren't powerful enough, but because their light literally hasn't arrived and may never arrive. The observable universe forms a sphere centered on Earth, with a radius of about 46.5 billion light-years. Yes, that's larger than 13.8 billion light-years because space itself has been expanding while light travelled toward us, stretching the distances involved. Everything beyond that boundary is invisible to us by definition. The actual universe, the total universe, is almost certainly far larger than the observable portion. It might be vastly larger. It might even be infinite. We simply don't know. But we can count what we can observe, and that observable volume contains approximately 2 trillion galaxies. Now comes the crucial calculation. If the observable universe contains roughly 2 trillion galaxies, and we want to know the total number of stars, we need to estimate the average number of stars per galaxy. This is where things become complicated because galaxies vary wildly in size and stellar population. The largest known galaxies, giant elliptical galaxies typically found at the centers of galaxy clusters, can contain over 100 trillion stars. These enormous systems form through multiple galactic mergers over billions of years, accumulating vast stellar populations. They're gravitationally bound cities of stars on a scale that dwarfs our Milky Way. At the opposite extreme, dwarf galaxies might contain only a few million, or even just a few thousand stars. These small, faint systems are incredibly difficult to detect but vastly outnumber giant galaxies. For every giant elliptical, there might be thousands of dwarf galaxies. Spiral galaxies like our Milky Way and our nearest large neighbour Andromeda typically contain anywhere from 100 billion to several hundred billion stars. Elliptical galaxies range from tiny dwarf ellipticals with millions of stars to massive ellipticals with trillions. Irregular galaxies, which lack organised structure, usually contain millions to tens of billions of stars. Most galaxies in the universe are small. Dwarf galaxies outnumber large galaxies by a significant margin. But large galaxies contain so many more stars that they dominate the total stellar census despite being numerically rare. It's like population distribution on Earth. Small towns outnumber major cities, but cities contain most of the population. When astronomers average across all galaxy types and sizes, accounting for the mix we observe, they estimate a typical galaxy contains somewhere between 100 million and 100 billion stars. For rough calculations, using 100 billion stars per average galaxy provides a reasonable middle ground that accounts for the mix of large and small systems. Let's do the mathematics. 2 trillion galaxies multiplied by 100 billion stars per galaxy equals 200 billion trillion stars. That's the answer. That's approximately how many stars exist in the observable universe based on our current best measurements and analysis. 200 billion trillion stars. Written out fully, that's 200,000, 1,000,000. In scientific notation, it's 2 × 1023. In words, it's 200 sextillion, though that name is rarely used because numbers this large transcend normal vocabulary. To put this number in perspective, let's return to our counting exercises. At 1 star per second, counting 200 billion trillion stars would require approximately 6.3 billion trillion years. The universe is only 13.8 billion years old. You'd need to count for roughly 457 million times longer than the current age of the universe just to count every star once. Let's try a different comparison. Scientists estimate that all of Earth's beaches combined contain approximately 7.5 quintillion grains of sand. That's 7,500,000 grains. It sounds like an enormous number, but the observable universe contains roughly 27 times more stars than Earth has grains of sand on all its beaches combined. Think about that for a moment. Every grain of sand on every beach, in every desert, across our entire planet represents not one star, but approximately 27 stars scattered across cosmic distances. Pick up a handful of sand, feel its weight, count the grains if you can. Now multiply that by 27 for every single grain. That's how many stars exist in the observable universe. Here's another way to conceptualize this magnitude. If you could somehow visit 1 star per second, travelling instantaneously with no time wasted between destinations, it would still take you 6.3 billion trillion years to visit every star. The universe will be cold, dark, and essentially dead long before you completed even a tiny fraction of that journey. If we could mobilize Earth's entire human population for this counting task, with all 8 billion people counting continuously at 1 star per second, it would still require approximately 792 trillion years to count every star in the observable universe. That's nearly 57,000 times the current age of the universe. These comparisons still fail to adequately convey the true magnitude because human cognition simply isn't equipped to process numbers this enormous. We can perform calculations with them. We can compare them mathematically to other large numbers, but we cannot intuitively grasp what 200 billion trillion actually means the way we grasp smaller quantities. The best we can do is recognize that the number transcends human intuition. entirely and exists in a realm of abstraction beyond visceral comprehension. Now let's add important nuance to this figure. The estimate of 200 billion trillion stars comes with significant uncertainties. We're extrapolating from observations of relatively nearby galaxies and applying those statistics across vast cosmic distances to regions we can barely observe. This involves multiple sources of potential error. First, our telescopes cannot detect all galaxies. We're certainly missing many of the smallest, faintest dwarf galaxies. Our estimate of 2 trillion galaxies probably undercounts the true population, possibly by a substantial factor. As telescope technology improves, this number will likely be revised upward, potentially dramatically. Second, our estimate of 100 billion stars per average galaxy carries considerable uncertainty. Different types of galaxies have vastly different stellar populations. The actual mix of galaxy types might differ in regions of the universe we cannot observe clearly. Both the galaxy count and the stars per galaxy average could be incorrect by factors of 2 or 3 or more. So our answer of 200 billion trillion stars might actually be 100 billion trillion, or it might be 400 billion trillion, or perhaps 500 billion trillion. The uncertainty doesn't diminish the extraordinary achievement of arriving at any answer at all. We're measuring the stellar census of the observable universe from one planet using instruments we designed and built. An uncertainty factor of 2 or 3 is remarkably impressive precision for such an audacious measurement. Moreover, this count of 200 billion trillion includes only the observable universe. The total universe almost certainly extends far beyond what we can observe. Beyond our cosmic horizon lie additional galaxies with additional stars that we can never detect because their light will never reach us. How many additional stars exist beyond the observable boundary? We cannot know. If the universe is infinite in extent, as some cosmological models suggest, then the total number of stars is also infinite. Our 200 billion trillion counts only what exists within the spherical region we can observe, a finite volume centered on Earth. The actual total could be vastly, perhaps infinitely larger. This raises profound questions about cosmic structure and the nature of existence itself. If the universe extends infinitely with roughly uniform properties, then everything that can happen will happen infinitely many times. There would be infinite copies of Earth, infinite versions of you, infinite variations on every possible arrangement of matter and energy. This seems philosophically troubling, but might be the reality we inhabit. Alternatively, the universe might be finite, but unimaginably larger than the observable portion. There might be 10 times more stars than we can count, or 1,000,000 times more, or 1,000,000,000,000 times more. We're fundamentally limited by the speed of light and the age of the universe. Information from sufficiently distant regions simply cannot reach us, rendering those regions forever beyond our knowledge. Let's explore what these 200 billion trillion observable stars actually represent. When we say star, we're describing objects that vary tremendously in their properties. Stars aren't uniform. They span an enormous range of masses, sizes, temperatures, colours, luminosities, and lifespans. At the lower extreme, we have red dwarf stars. These are the smallest stars capable of sustaining stable hydrogen fusion, with masses around 0.08 to 0.5 times the Sun's mass. Below 0.08 solar masses, you get brown dwarfs, failed stars that never achieve the core temperatures necessary for sustained fusion. Brown dwarfs glow dimly from residual heat but aren't true stars. Red dwarfs are tiny, cool, and extraordinarily dim compared to larger stars. The smallest ones have surface temperatures around 2,500 Kelvin, giving them a deep red colour. They produce so little light that none are visible to the naked eye, despite being the most common type of star. The nearest red dwarf to Earth, Proxima Centauri, requires a telescope to observe despite being only 4.24 light-years away. What makes red dwarfs remarkable is their longevity. They burn hydrogen so slowly and efficiently that they can live for trillions of years. The smallest red dwarfs might have lifespans of 10 trillion years or more. That's approximately 700 times longer than the current age of the universe. Not a single red dwarf that ever formed has yet died. The universe simply isn't old enough. These stars will still be burning steadily long after every other type of star has exhausted its fuel and gone dark. Despite their individual dimness, red dwarfs constitute approximately 70 to 75% of all stars. 3/4 of the stellar population consists of these small, long-lived, nearly invisible objects. If we could suddenly perceive all red dwarfs in our region of the galaxy, the night sky would be transformed. Thousands of faint red stars would appear where currently we see only dozens of bright stars. At the opposite extreme lie the massive stars, blue and white supergiants with masses ranging from 20 to over 100 times the Sun's mass. These stellar monsters burn incredibly hot and bright. Their surface temperatures can exceed 30,000 Kelvin, giving them an intense blue-white colour. A single massive star can emit more light than 1,000,000 red dwarfs combined. But massive stars live fast and die spectacularly young. A star with 20 solar masses might live only 10 million years. A star with 50 solar masses might last just 4 million years. The most massive stars known, approaching or exceeding 100 solar masses, burn through their nuclear fuel in merely a few million years before ending their lives in catastrophic supernova explosions. These massive stars are extremely rare. For every massive blue supergiant, there might be thousands or tens of thousands of red dwarfs. But massive stars are so luminous that they dominate the visible appearance of galaxies. When you look at a galaxy through a telescope, you're seeing primarily the light from its most massive, brightest stars, not the dim red dwarfs that actually constitute most of its stellar population. Between these extremes lie intermediate mass stars like our Sun. The Sun has approximately 1 solar mass, by definition, and a surface temperature around 5800 Kelvin, giving it a yellowish-white colour. It will live for approximately 10 billion years total. The Sun has already existed for about 4.6 billion years and will continue burning steadily for another 5 to 6 billion years before exhausting its hydrogen fuel. Stars like our Sun constitute perhaps 7 to 10% of all stars. They're not the most common type, but neither are they particularly rare. Our Sun is actually above average in mass and luminosity. Most stars are smaller and dimmer. If you randomly selected a star from our galaxy, you'd most likely pick a red dwarf. If you randomly selected a visible star from the night sky, you'd more likely pick something larger and brighter than the Sun because those stars are easier to see despite being rarer. Stars also exist in different evolutionary stages. Young stars, recently formed from collapsing gas clouds, are often surrounded by disks of leftover material from which planets may form. These protoplanetary disks can persist for millions of years, while planets coalesce from the orbiting dust and gas. Middle-aged stars like our Sun exist in a stable phase called the main sequence, where they burn hydrogen steadily in their cores, converting it to helium through nuclear fusion. This is the longest phase of stellar life, lasting billions of years for Sun-like stars. Old stars have exhausted the hydrogen in their cores and begin fusing helium and heavier elements. They swell dramatically into red giants, expanding to many times their original size. When our Sun becomes a red giant in about 5 billion years, it will expand beyond Earth's current orbit, engulfing Mercury and Venus, and possibly Earth itself. Eventually stars die, though the manner of death depends critically on mass. Low-mass stars like red dwarfs will theoretically live so long that none have died yet. When they finally do exhaust their fuel trillions of years from now, they'll likely just fade away, cooling slowly into black dwarfs. Medium-mass stars like our Sun will become red giants, then shed their outer layers in beautiful planetary nebulae, leaving behind white dwarfs. These white dwarfs are incredibly dense, Earth-sized remnants with masses comparable to the Sun but packed into a volume the size of a planet. They glow from residual heat and slowly cool over trillions of years. Massive stars die catastrophically. When they've fused elements all the way to iron in their cores, fusion stops because iron fusion requires energy input rather than releasing energy. Without fusion pressure to counteract gravity, the core collapses in less than a second, triggering a supernova explosion that briefly outshines entire galaxies. The core collapses into either a neutron star or, if massive enough, a black hole. When we count 200 billion trillion stars, we're counting all these types and evolutionary stages. Young stars still forming from gas clouds, middle-aged stars like our Sun burning steadily, old red giants nearing the end of their lives, white dwarfs cooling slowly, neutron stars and black holes the remnants of massive stars, binary systems where two stars orbit each other, multiple star systems with 3 or more gravitationally bound stellar companions. We're counting the full diversity of stellar evolution across the observable universe. This matters for several crucial reasons that connect directly to our own existence. First, stars are the universe's element factories. The Big Bang produced primarily hydrogen and helium, with trace amounts of lithium. Everything heavier than those light elements was created in stars through nuclear fusion. Carbon, nitrogen, oxygen, silicon, iron, gold, uranium, every element heavier than helium was forged in stellar cores or in supernova explosions. The first generation of stars that formed after the Big Bang consisted almost entirely of primordial hydrogen and helium. These population 3 stars, as astronomers call them, were likely very massive and short-lived. They fused hydrogen into helium, then helium into carbon and oxygen, continuing up the periodic table to create heavier elements in their cores. When these massive first-generation stars exploded as supernovae, they scattered their newly forged elements into space, enriching the interstellar medium. The second generation of stars formed from gas clouds that contained these heavy elements. These population 2 stars continued the process, creating more heavy elements and distributing them through supernova explosions. By the third generation, population 1, stars like our Sun, the interstellar medium had been significantly enriched with heavy elements. Our Sun formed from a molecular cloud that contained carbon, oxygen, nitrogen, silicon, iron, and other heavy elements created by previous stellar generations. This means every atom in your body heavier than hydrogen was created in a star that lived and died before our Sun formed. The calcium in your bones was forged in stellar cores billions of years ago. The iron in your blood was created in supernova explosions. The oxygen you breathe, the carbon in your DNA, the nitrogen in your proteins, all were manufactured by stars. You're not just figuratively stardust, you're literally assembled from atoms that were synthesized in stars, scattered by stellar deaths, incorporated into the molecular cloud that formed our solar system, and eventually arranged into the complex biochemical structures that constitute you. Every breath involves atoms with a cosmic history spanning billions of years. Second, the stellar census tells us about planet formation. For most of human history, we had no idea whether planets existed around other stars. We knew our solar system had planets, but were they common or rare? Did most stars have planetary systems, or was our Sun special? In the 1990s, astronomers began detecting the first exoplanets, planets orbiting stars other than our Sun. The discoveries came slowly at first, then accelerated rapidly as detection techniques improved. Today, we've confirmed over 5,000 exoplanets, with thousands more candidates awaiting confirmation. What we've learned is revolutionary. Planets are not rare. They're ubiquitous. Most stars have planets. Some have multiple planets. Some have dozens. The galaxy is filled with planetary systems of staggering diversity. We found hot Jupiters, massive gas giants orbiting closer to their stars than Mercury orbits our Sun. We found super-Earths, rocky planets larger than Earth but smaller than Neptune. We found ocean worlds that might be entirely covered in water. We found planets orbiting binary star systems. We found rogue planets wandering through interstellar space, unbound to any star. Statistical analysis of exoplanet surveys suggests that, on average, there's at least one planet per star. Some estimates suggest closer to 2 or 3 planets per star on average. If we conservatively estimate 1 planet per star, the observable universe contains at least 200 billion trillion planets. That's a minimum estimate. The actual number could be significantly higher. 200 billion trillion worlds. Some are gas giants like Jupiter and Saturn. Some are ice giants like Uranus and Neptune. Some are rocky worlds like Earth, Mars, Mercury and Venus. They span an incredible range of sizes, compositions, orbital configurations, and environmental conditions. Some of these planets orbit within their star's habitable zone, the range of distances where temperatures allow liquid water to exist on a planetary surface. Water is essential for life as we know it. A planet in the habitable zone with the right atmospheric composition and geological activity might potentially support life. How many planets orbit in habitable zones? Estimates vary, but surveys suggest perhaps 20 to 50% of Sun-like stars have at least one planet in the habitable zone. For red dwarfs, which are the most common stars, the percentage might be similar or even higher, though the habitable zone is much closer to the star due to the star's dimness. Let's be conservative and say 20% of stars have a potentially habitable planet. That's 40 billion trillion potentially habitable worlds in the observable universe. Even if only 1 in a billion of those actually develops life, that's still 40 trillion living worlds. If only 1 in a million of those develops intelligent life, that's 40 million technological civilizations. These numbers are highly speculative. We don't know the probability of life arising on a suitable planet. We don't know the probability of simple life evolving into complex life. We don't know the probability of complex life developing intelligence and technology. These are open questions in astrobiology. But the sheer number of opportunities is staggering. Even if life is extraordinarily rare, the vast number of planets means it might exist in many places simply because there are so many chances for it to arise. Third, the stellar population informs our understanding of cosmology and the universe's composition. When astronomers measure the total mass of galaxies using gravitational effects, they find something puzzling. The visible stars and gas account for only a small fraction of the total mass. The rest is dark matter, an invisible form of matter that doesn't emit or absorb light but exerts gravitational influence. The universe's mass-energy composition is roughly 5% ordinary matter, the stuff that stars and planets and we are made from. 27% dark matter, whose nature remains mysterious, and 68% dark energy, an even more mysterious form of energy, causing the universe's expansion to accelerate. Those 200 billion trillion stars, despite seeming incredibly numerous, represent only a fraction of the universe's ordinary matter. Much ordinary matter exists as gas between stars and galaxies, in diffuse intergalactic clouds, or in compact objects like white dwarfs, neutron stars, and black holes. And all ordinary matter combined is dwarfed by dark matter and dark energy. Understanding the stellar population helps us map the distribution of ordinary matter and constrains models of galaxy formation and evolution. It reveals how matter has organized itself over cosmic history under the influence of gravity and cosmic expansion. Let's consider stellar density and the distances between stars. In our region of the Milky Way, the nearest star to our Sun is Proxima Centauri, about 4.24 light-years away. That's approximately 25 trillion miles or 40 trillion kilometers. Space is overwhelmingly empty. The distances between stars are vast compared to the stars themselves. The Sun's diameter is about 1.4 million kilometers. The distance to Proxima Centauri is about 28 million times larger than the Sun's diameter. If you scaled the Sun down to the size of a grain of sand 1 millimeter across, Proxima Centauri would be another grain of sand 28 kilometers away. Most of space consists of near-perfect vacuum between these widely scattered stellar grains. This isn't universally true. In the dense cores of globular clusters, ancient spherical collections of stars orbiting galaxies, stellar density is much higher. In some globular cluster cores, stars are separated by only a few light weeks or light months, still vast by human standards but densely packed astronomically. In the galactic center, stellar density is also significantly elevated. But in most of the universe, in the spiral arms and outer regions of galaxies, in the space between galaxies, stars are separated by distances that make interstellar travel extraordinarily challenging. Even traveling at the speed of light, which physics tells us is impossible for anything with mass, it would take 4.24 years to reach the nearest star from Earth. At more achievable speeds, say 10% of light speed, which is still far beyond our current technological capabilities, the journey would take 42 years. Crossing our entire galaxy at that speed would take 1,000,000 years. Crossing the space to Andromeda, our nearest large galactic neighbour, would take 25 million years. Those 200 billion trillion stars are scattered across such immense volumes that despite their enormous number, the universe remains mostly empty space. Now let's address whether star formation is ongoing, or if 200 billion trillion represents a fixed final count. Stars are still forming today throughout the universe. In molecular clouds throughout galaxies, gravity continues pulling gas together into dense clumps that eventually collapse and ignite fusion, becoming new stars. Our Milky Way forms approximately 1 to 3 new stars per year on average. That might seem like a lot, but compared to the existing population of 200 billion stars, it's a negligible addition rate. At that rate, it would take hundreds of billions of years to significantly increase the galaxy's stellar population. Different galaxies have vastly different star formation rates. Some small elliptical galaxies have exhausted their gas supplies and no longer form stars at all. They're filled with old stars slowly aging toward their eventual demise. Other galaxies, particularly irregular galaxies undergoing starbursts, might produce hundreds or thousands of new stars per year. Galaxy collisions and interactions can trigger intense bursts of star formation. When two galaxies merge, their gas clouds collide and compress, triggering rapid collapse into new stars. Some colliding galaxies produce thousands of new stars annually during these merger events. Across the entire observable universe, the total star formation rate is difficult to measure precisely, but estimates suggest approximately 100 to 300 stars form per second in all galaxies combined. That sounds impressive until you compare it to the existing population. Even at 300 stars per second, it would take over 20 billion years to double the current stellar population, longer than the universe's current age. Moreover, the universe's star formation rate has been declining for billions of years. The peak of cosmic star formation occurred roughly 10 billion years ago, when the universe was about 3 to 4 billion years old. Since then, galaxies have gradually consumed their available gas, and the star formation rate has steadily decreased. Eventually, in the distant future, perhaps 100 trillion years from now, star formation will cease entirely. Galaxies will have exhausted their gas supplies. No new stars will form. The existing stellar population will age. Red dwarfs will continue burning for trillions of years, but more massive stars will die and become white dwarfs, neutron stars, or black holes. Slowly, over incomprehensible timescales, the galaxies will dim as their stars go dark one by one. This won't happen soon by any human timescale. We're living in what cosmologists call the stelliferous era, the age when stars shine. This era began a few 100 million years after the Big Bang, when the first stars ignited, and it will continue for tens or hundreds of trillions of years until the last stars finally exhaust their fuel. We're actually quite early in the stelliferous era. The vast majority of stellar lifetimes, particularly the trillion-year lifespans of red dwarfs, still lies ahead. Most of cosmic history, the preponderance of time, will occur after stars have gone dark. But that's unimaginably far in the future, incomprehensibly distant from our current moment in cosmic time. This illustrates that 200 billion trillion isn't a fixed, eternal number. It's a snapshot of the current stellar population at this moment in cosmic history. In the past, fewer stars existed. In the future, the number will increase for a while, as new stars continue forming, then eventually decrease as old stars die faster than new ones form. Let's talk about how astronomers actually count galaxies and estimate stellar populations. It's obviously not like counting cars in a parking lot where you can observe each one individually and tally them. The process involves sophisticated statistical sampling, combined with theoretical models of stellar populations and galaxy formation. Deep surveys like the Hubble Deep Field pointed powerful telescopes at tiny patches of seemingly empty sky for days or weeks, detecting extremely faint distant galaxies. By counting galaxies in those small patches and extrapolating that density across the entire celestial sphere, astronomers estimated the total galaxy count. More recent surveys have employed different strategies. Wide-field surveys observe much larger areas of sky but don't go as deep, missing the faintest, most distant galaxies. By combining wide and deep surveys, astronomers build a more complete census that accounts for both bright nearby galaxies and faint distant ones. Estimating the number of stars per galaxy requires observing galaxies at various distances and of different types, measuring their total light output, and using models of stellar populations to estimate how many stars of different types would produce that observed light. A galaxy's total luminosity depends critically on its stellar population composition. Young populations dominated by massive luminous stars are very bright. Old populations dominated by red dwarfs and aging low-mass stars are much dimmer. By analysing galaxy spectra, the detailed distribution of wavelengths in their light, astronomers can estimate the ages and compositions of stellar populations. These measurements all contain uncertainties. Interstellar dust within galaxies absorbs and scatters light, making galaxies appear dimmer than they actually are. Distance measurements to remote galaxies have uncertainties that propagate through calculations. Models of stellar populations involve assumptions about star formation history and the initial mass function, the distribution of stellar masses at birth. Despite these uncertainties, multiple independent methods yield broadly consistent results. When different techniques converge on similar answers, it increases confidence that we're measuring something real rather than seeing artifacts of our measurement methods. The estimate of 200 billion trillion stars emerges from this convergence of evidence, not from a single observation or calculation. This is how science operates at cosmic scales. We cannot directly measure everything. We must combine observations with theoretical models and statistical reasoning. The remarkable thing is that it works. Our estimates are probably accurate to within a factor of 2 or 3, which for such an audacious measurement spanning the observable universe is impressively precise. Let's appreciate the technology that makes these measurements possible. Humanity's ability to count cosmic objects depends entirely on our instruments. The naked eye sees thousands of stars. Galileo's crude refracting telescope revealed thousands more. Modern instruments have expanded our view by factors of trillions. The Hubble Space Telescope, orbiting above Earth's atmosphere and avoiding atmospheric distortion, can detect objects so distant their light has travelled for over 13 billion years to reach us. Its deep field images revealed galaxies that formed when the universe was less than 1 billion years old in its early infancy. Ground-based telescopes, equipped with adaptive optic systems that compensate for atmospheric turbulence in real time, achieve remarkable image clarity, rivaling space-based instruments for some observations. The largest ground-based telescopes have mirrors 8 to 10 meters in diameter, collecting vast amounts of light and enabling detection of incredibly faint objects. Radio telescopes detect emissions at radio wavelengths invisible to optical instruments. Radio observations reveal different aspects of cosmic objects, including cold gas clouds, active galactic nuclei, and the large-scale structure of galaxy distributions across cosmic distances. X-ray and gamma-ray telescopes, which must operate from space because Earth's atmosphere blocks these high-energy wavelengths, reveal violent processes like matter falling into black holes, neutron stars colliding, and the hot gas between galaxies and galaxy clusters. The James Webb Space Telescope, launched in December 2021, observed primarily in infrared wavelengths. Infrared light can penetrate dust clouds that block visible light, revealing star formation, regions hidden from optical observation. Infrared observations also detect extremely distant galaxies whose light has been redshifted by cosmic expansion from ultraviolet and visible wavelengths into the infrared. Future telescopes, both ground-based and space-based, will push observations even further. The extremely large telescope under construction in Chile will have a 39-meter primary mirror, the largest optical telescope ever built. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct wide-field infrared surveys, mapping large portions of sky to create unprecedented galaxy catalogues. With each technological improvement, we refine our cosmic census. We discover galaxies we previously missed. We measure distances more accurately. We better understand stellar populations and galaxy evolution. The estimate of 200 billion trillion stars will likely be revised as our instruments improve, though probably not by orders of magnitude. We've reached the point where our measurements are capturing most of what's observable. Now let's return to the philosophical implications of this number. 200 billion trillion stars scattered across the observable universe. What does this mean for us, for humanity, for our place in existence? First, it provides stark perspective on our cosmic significance. Earth orbits one star among 200 billion trillion. Our Sun is thoroughly ordinary, neither especially massive nor especially small, neither especially young nor especially old, neither especially bright nor especially dim. It's utterly typical, one star among countless multitudes. If our Sun vanished tomorrow, the universe would not notice. The cosmic impact would be zero. The vast machinery of cosmic evolution would continue unchanged. Those 200 billion trillion stars would keep burning. Galaxies would keep orbiting. The universe would keep expanding, all without the slightest awareness that one average star had ceased to exist. This can feel diminishing, even frightening. We're infinitesimally small in a cosmos of incomprehensible scale. Our entire history, all of human civilization, every person who ever lived, exists on one small planet orbiting one ordinary star in one typical galaxy among trillions. But there's another way to interpret this reality. We exist despite overwhelming improbability. The fact that conscious, intelligent, technological life arose on a planet orbiting an ordinary star among 200 billion trillion demonstrates that the universe is capable of producing extraordinary complexity and awareness from simple physical laws operating across cosmic time. We're not cosmically important in terms of scale, mass, or gravitational influence. The universe doesn't revolve around us. Earth isn't the centre of anything. But we're remarkable in a different and perhaps more meaningful sense. We're matter organised in such complex ways that we can perceive, think, feel, and understand. We're the universe's way of knowing itself, conscious patterns contemplating our own cosmic origins. Second, these numbers raise profound questions about extraterrestrial life. With 200 billion trillion stars, many hosting planets, potentially trillions of worlds, orbiting in habitable zones, the question shifts from does life exist elsewhere to how common is it and will we ever detect it? If life arises readily given suitable conditions, the universe might be teeming with living worlds. There could be billions or trillions of planets hosting life right now. Some might harbour simple microbial life, others might have complex ecosystems. Perhaps some have developed intelligence and technology. If intelligent life is reasonably common, there could be millions or even billions of technological civilizations scattered across cosmic distances. They might be asking the same questions we're asking, looking up at their own night skies, wondering if they're alone. The Fermi paradox asks, if life should be common given the vast number of stars and planets, why haven't we detected any signs of alien civilizations? Where is everybody? Several possible answers exist, each with different implications. Perhaps life is extraordinarily rare. Maybe the transition from chemistry to biology requires such specific conditions that it almost never happens. Earth might be one of very few living worlds, possibly the only one in the observable universe. That seems statistically unlikely given 200 billion trillion stars, but we can't rule it out with certainty. Perhaps life is common, but intelligence is rare. Life on Earth existed as simple single-celled organisms for about 3 billion years before complex multicellular life evolved. Intelligence and technology emerged very recently. Maybe most living worlds never progressed beyond microbial life. Perhaps intelligent civilizations are common but short-lived. Maybe technological species inevitably destroy themselves through war, environmental collapse, or other catastrophes before becoming detectable across interstellar distances. This is a sobering possibility with implications for our own future. Perhaps space is simply too vast. Even if millions of civilizations exist, they might be separated by such enormous distances that communication or contact is impossible. Light speed limits prevent rapid information exchange. A civilization 10,000 light-years away wouldn't receive radio signals we broadcast today for 10,000 years. We wouldn't receive their reply for another 10,000 years. Meaningful dialogue becomes impossible across such timescales. We're searching for answers. Radio telescopes scan for artificial signals that might indicate technological activity. The search for extraterrestrial intelligence has monitored millions of stars without detecting convincing signals. But we've barely begun sampling the possibilities. We're also analysing exoplanet atmospheres for biosignatures, chemical compositions that might indicate biological activity. Oxygen in Earth's atmosphere is a biosignature. It's highly reactive and would quickly combine with other elements if not constantly replenished by photosynthesis. An exoplanet with abundant atmospheric oxygen might harbour photosynthetic life. The James Webb Space Telescope can study some exoplanet atmospheres in unprecedented detail. Future dedicated missions will do even better. Within decades, we might detect chemical evidence of life on another world. Or we might find nothing despite comprehensive searches, suggesting life is rarer than we hoped. Either answer would be profound. Finding life elsewhere would tell us we're not alone, that the universe produces life wherever conditions allow. Finding nothing despite exhaustive searches would reveal how rare and precious life is, how special Earth might be, how much responsibility we bear to preserve and protect the one known living world. Third, these enormous numbers challenge our ability to create meaning in what appears to be an indifferent cosmos. Humans naturally create meaning through connections, relationships, achievements, and stories. We care deeply about family, friends, accomplishments, creative works, and love. The question becomes, does any of this matter in a universe containing 200 billion trillion stars? Some people find the cosmic scale deeply troubling. If we're so insignificant, so infinitesimally small compared to the vastness of space and time, how can anything we do possibly matter? Your worst day, your greatest triumph, your most embarrassing moment, your proudest achievement, all occur on one tiny planet orbiting one ordinary star among incomprehensible multitudes. From a cosmic perspective, none of it registers. But there's a different way to interpret this reality, one that's liberating rather than diminishing. The universe is so vast that your personal concerns, which can feel overwhelming when you're experiencing them, become smaller and more manageable when viewed against cosmic scale. That argument you had, that mistake you made, the opportunity you missed, none of it echoes across the universe. You're free to live, to make mistakes, to try again, to create meaning on your own human terms without cosmic judgment. The stars don't care about your failures or successes, and there's freedom in that indifference. You're not performing for a cosmic audience. You're not being judged by the universe. You can define success and meaning for yourself, create your own values, build connections that matter to you regardless of their cosmic significance. Others find cosmic scale deeply motivating rather than troubling. We exist for such a brief time in such an incomprehensibly vast cosmos. That temporal and spatial brevity makes our existence precious rather than meaningless. We have limited time to experience, learn, create, connect, and contribute. Why waste it on trivial concerns? Why not embrace the extraordinary opportunity we have to be conscious, aware, and capable of experiencing wonder? The cosmic perspective can inspire urgency to make the most of our temporary existence. We won't be here forever. The universe will continue long after we're gone. That makes right now, this moment, precious beyond measure. The people you care about won't be here forever. The opportunities you have won't last indefinitely. The cosmic scale reminds us to appreciate what we have while we have it. There's no single correct emotional response to cosmic scale. Awe, humility, insignificance, liberation, motivation, all are valid reactions. The key is integrating this knowledge into your worldview in a way that enriches rather than diminishes your life. Understanding that 200 billion trillion stars exist shouldn't paralyze you with existential dread. It should expand your sense of wonder while simultaneously grounding your daily concerns in appropriate perspective. Let's talk about cosmic structure and how those 200 billion trillion stars are organized. Stars don't exist in random isolation, scattered uniformly through space. They cluster into galaxies. Galaxies cluster into groups and clusters. Clusters organize into superclusters, and superclusters form the largest known structures in the universe, the cosmic web of filaments and voids that stretches across observable space. This hierarchy of structure exists because of gravity operating across cosmic time. After the Big Bang, matter was distributed almost but not quite uniformly. There were tiny density fluctuations, quantum variations from the very early universe that got stretched to cosmic scales during the brief period of cosmic inflation. Regions that were slightly denser than average had slightly stronger gravitational pull. They attracted surrounding matter. As matter accumulated in these regions, their gravity strengthened further. This created a positive feedback loop. Dense regions became denser, pulling in more matter from their surroundings. The voids between dense regions became emptier as their matter was gravitationally pulled away. Over hundreds of millions and billions of years, this process amplified those tiny initial fluctuations into the large-scale structure we observe today. If you could somehow observe the entire observable universe at once, you'd see a foam-like or web-like pattern, dense filaments of galaxies surrounding vast empty voids. The filaments intersect at nodes where massive galaxy clusters reside. The largest individual structures, the supercluster complexes, span hundreds of millions of light-years. Our Milky Way galaxy belongs to a collection of about 80 galaxies called the Local Group. The Local Group includes our largest neighbour, the Andromeda Galaxy, the smaller Triangulum Galaxy, and dozens of dwarf galaxies. The entire Local Group spans approximately 10 million light-years across. The Local Group itself is part of the Virgo supercluster, which contains thousands of galaxies organised into hundreds of smaller groups and clusters. The Virgo supercluster spans roughly 110 million light-years, and the Virgo supercluster is part of an even larger structure called Laniakea, a supercluster complex containing about 100,000 galaxies across 520 million light-years. Laniakea isn't the largest structure either. It's one supercluster among many in the observable universe. The largest known structures are the galaxy filaments and walls, vast sheets and strings of galaxies hundreds of millions of light-years long. This cosmic structure formed through purely gravitational processes, amplifying tiny initial density variations. Those variations originated in the first fraction of a second after the Big Bang, quantum fluctuations that occurred during cosmic inflation. Everything we see today, every galaxy, every star, every structure, traces its origins to quantum effects from the universe's first moments. The 200 billion trillion stars we've counted are organised into this vast gravitational architecture. They're not randomly distributed. They follow patterns established billions of years ago, patterns we can map and measure and understand through careful observation and theoretical modelling. Now let's address the cosmic future and what will happen to those 200 billion trillion stars over incomprehensible timescales. Stars don't shine forever. They have finite lifetimes determined primarily by their mass. We've discussed this briefly already, but let's examine it in more depth. Massive stars burn through their fuel quickly. A star with 60 solar masses might live only 3 million years from formation to supernova. A star with 30 solar masses might last 10 million years. These are cosmically brief lifespans, barely a moment compared to the current age of the universe. Stars similar to our Sun, with approximately 1 solar mass, live about 10 billion years. Our Sun has existed for 4.6 billion years and will continue burning hydrogen for another 5 billion years or so. Then it will swell into a red giant, fuse helium for perhaps 1 billion more years, and finally shed its outer layers to become a white dwarf. Red dwarfs, the smallest true stars, live far longer. A red dwarf with 0.1 solar masses might burn steadily for 10 trillion years. Some of the smallest red dwarfs might have lifespans exceeding 10 trillion years, nearly 1,000 times longer than the universe's current age. This means no red dwarf has ever died. Every red dwarf that formed in the first few 100 million years after the Big Bang is still burning today, still fusing hydrogen, still shining. They'll continue shining long after every other type of star has exhausted its fuel and gone dark. The universe's star formation rate has been declining for billions of years, as we discussed. The peak of cosmic star formation occurred roughly 10 billion years ago. Since then, galaxies have consumed their gas supplies, and the formation rate has steadily decreased. Eventually, star formation will cease entirely. Current models suggest the last stars will form perhaps 100 trillion years from now, possibly earlier depending on detailed galaxy evolution models. From that point forward, the stellar population will only decrease. No new stars will form. Existing stars will age and die. Massive stars will continue exploding as supernovae for millions of years, leaving behind neutron stars and black holes. Medium-mass stars will become white dwarfs over billions of years. Red dwarfs will burn for trillions of years before finally exhausting their fuel. Eventually, perhaps 100 trillion years from now, maybe sooner, the last main sequence star will exhaust its hydrogen and leave the main sequence. The universe will enter what cosmologists call the degenerate era, an age dominated by stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs will slowly cool over trillions of years, eventually becoming black dwarfs, cold, dark stellar remnants no longer emitting detectable radiation. This process takes incomprehensibly long. The universe isn't old enough for any black dwarfs to exist yet. On even longer timescales, perhaps 10 or 30 to 1040 years from now, stellar remnants might be ejected from galaxies through gravitational interactions, or they might spiral into the supermassive black holes at galactic centers. Galaxies themselves might evaporate as stars are flung into intergalactic space through many-body gravitational interactions. On still longer timescales, perhaps 10 or 100 years, even black holes evaporate through Hawking radiation, a quantum effect that causes black holes to slowly lose mass and eventually disappear. When the last black holes finally evaporate, the universe will contain only diffuse radiation, fundamental particles, and possibly some exotic remnant objects. This future is unimaginably remote, incomprehensibly distant from our current moment. We're living in what cosmologists call the stelliferous era, the age when stars shine. This is a relatively brief phase in cosmic history, lasting perhaps 100 trillion years total. But we're early in this phase. Most stars that will ever exist haven't formed yet. Most stellar lifetimes still lie ahead. After the stelliferous era comes the degenerate era, the black hole era, and finally the dark era when even black holes have evaporated and the universe consists of nearly motionless particles separated by incomprehensible distances in a cold, dark, ever-expanding void. But that's the far future, trillions upon trillions of years away. For now, the universe is vibrant with starlight. Those 200 billion trillion stars illuminate the cosmos, creating the spectacular night skies we can observe and measure and appreciate. Let's return to the question of how we actually know all this. How do astronomers count galaxies, estimate stellar populations, measure cosmic distances, and determine the age and composition of the universe? The answer reveals the extraordinary power of combining careful observation with theoretical understanding. Counting galaxies, as we've discussed, involves deep surveys that observe tiny patches of sky for extended periods, detecting faint distant galaxies. The Hubble Deep Field and its successors revealed thousands of galaxies in regions that appeared empty to previous observations. By extrapolating the density of galaxies in these small regions to the entire sky, astronomers estimate the total galaxy population. But this process isn't simple extrapolation. Different types of surveys detect different types of galaxies. Deep, narrow surveys like the Hubble Deep Field excel at finding faint, distant galaxies but cover tiny areas. Wide, shallow surveys cover larger areas but miss faint objects. Combining multiple survey types creates a more complete picture. Astronomers also must account for selection effects. Bright galaxies are easier to detect, so surveys preferentially find them. Small, faint dwarf galaxies vastly outnumber large galaxies, but are much harder to detect. Statistical models account for the galaxies we're missing based on what we can observe about galaxy populations and their distributions. Estimating stars per galaxy requires understanding stellar populations. When we observe a galaxy, we're seeing its total light output. That light comes from billions or trillions of individual stars, each contributing based on its luminosity. But we can't count stars individually in distant galaxies. We must infer stellar populations from the galaxy's total light and its spectrum. A galaxy's spectrum reveals the distribution of wavelengths in its light. Young stellar populations dominated by massive hot stars produce light rich in blue and ultraviolet wavelengths. Old populations dominated by small cool stars produce light rich in red and infrared wavelengths. By analysing spectra, astronomers estimate the ages and compositions of stellar populations. Stellar population models combine our understanding of stellar evolution with observations of nearby star clusters to predict how populations of different ages and compositions should appear. By comparing galaxy observations to these models, astronomers estimate how many stars of different types must exist to produce the observed light. These measurements all contain uncertainties. Interstellar dust absorbs and scatters light, particularly at blue and ultraviolet wavelengths. This makes galaxies appear redder and dimmer than they actually are. Astronomers must correct for dust extinction, but these corrections are imperfect. Distance measurements introduce additional uncertainty. For nearby galaxies, we can measure distances using standard candles, like Cepheid variable stars, whose pulsation periods reveal their intrinsic luminosity. By comparing intrinsic and apparent luminosity, we calculate distance. For more distant galaxies, we use other techniques. Type Ia supernovae, which have relatively consistent peak luminosities, serve as standard candles for vast distances. The redshift of galaxy light caused by cosmic expansion stretching wavelengths reveals recession velocity. Hubble's law relates recession velocity to distance. Each method has calibration uncertainties and systematic errors. Different techniques sometimes yield slightly different distances to the same object, but they generally agree within uncertainties, creating confidence that we're measuring real distances rather than artifacts of our methods. All these measurements combine to yield our estimate of 200 billion trillion stars. This number represents convergence of multiple independent lines of evidence. It's not based on a single observation or calculation, but on decades of refinement through increasingly sophisticated observations and theoretical understanding. Let's appreciate the remarkable tools that make these measurements possible. The Hubble Space Telescope orbits Earth above the atmosphere, avoiding atmospheric distortion that blurs ground-based observations. Its position allows it to stare at the same patch of sky for days or weeks, collecting every possible photon to reveal the faintest, most distant objects. Hubble's observations have been transformative. The deep fields revealed galaxies so distant, their light has travelled for over 13 billion years. We're seeing these galaxies as they appeared when the universe was less than 1 billion years old, shortly after the first stars formed. Hubble showed us the universe in its infancy, revealing how galaxies evolved over cosmic time. ground-based telescopes have also achieved remarkable capabilities. Adaptive optics systems use deformable mirrors that change shape hundreds or thousands of times per second, compensating for atmospheric turbulence. These systems allow ground-based telescopes to achieve image clarity rivaling space telescopes for some observations. The largest ground-based optical telescopes have primary mirrors 8 to 10 meters in diameter. The Gran Telescopio Canarias has a 10.4 meter mirror. The two Keck telescopes each have 10-meter mirrors. These enormous light-gathering surfaces can detect extremely faint objects and study them in detail. Radio astronomy reveals different aspects of the cosmos. Radio telescopes detect emissions at radio wavelengths invisible to optical instruments. Radio observations map cold gas clouds where stars form, reveal active galactic nuclei powered by supermassive black holes, and trace the large-scale distribution of matter across cosmic distances. The Atacama Large Millimeter Submillimeter Array, ALMA, consists of 66 radio dishes working together as a single instrument. ALMA observes at millimeter and submillimeter wavelengths, revealing dusty star-forming galaxies invisible at optical wavelengths, and studying the molecular clouds where stars and planets form. X-ray astronomy requires space-based telescopes because Earth's atmosphere blocks X-rays. The Chandra X-ray Observatory and XMM Newton reveal high-energy processes like matter spiraling into black holes, neutron stars colliding, and the hot gas between galaxies and galaxy clusters. The James Webb Space Telescope, launched in December 2021, represents the current frontier of space astronomy. Its 6.5-meter mirror, much larger than Hubble's 2.4-meter mirror, collects far more light. Its infrared instruments can see through dust clouds and detect the most distant galaxies yet observed. Webb's early observations have already revealed galaxies that existed when the universe was only a few 100 million years old, earlier than many models predicted. As Webb continues operating, it will refine our understanding of galaxy formation, star formation, and the chemical evolution of the cosmos. Future missions will push observations even further. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct wide-field infrared surveys, mapping large areas of sky to unprecedented depths. The European Space Agency's Euclid mission will map the large-scale structure of the universe and study dark energy. Ground-based, extremely large telescopes currently under construction will have primary mirrors 30 to 40 meters in diameter. These enormous instruments will collect even more light, enabling detailed study of exoplanet atmospheres, the first stars and galaxies, and the chemical compositions of distant stellar populations. With each technological advance, we refine our cosmic census. We discover galaxies we missed. We measure distances more precisely. We better understand stellar populations and galaxy evolution. The estimate of 200 billion trillion stars will likely change as our instruments improve, but probably not by orders of magnitude. We've reached a level of observational capability where we're detecting most of what's observable. Now let's reflect on what this means for us personally and collectively. When you go outside tonight and look up at the stars, you'll see perhaps 2,000 to 4,000 individual points of light, depending on your location and sky conditions. But now you know those visible stars are floating in a vast sea of 200 billion in our galaxy alone. And our galaxy is one of 2 trillion galaxies, collectively containing approximately 200 billion trillion stars. Each visible star is a massive nuclear furnace fusing hydrogen into helium and light. Each one likely has planets orbiting it, some potentially inhabitable zones where liquid water could exist. Each one is part of the grand cosmic narrative of matter and energy evolving across billions of years. The light entering your eyes has travelled across space for years or centuries or millennia. When you look at Proxima Centauri, you're seeing light that left the star 4.24 years ago. When you look at more distant stars, you're seeing light that departed decades, centuries, or millennia ago. You're looking into the past, observing stars as they were when that light began its journey. You're connected to those distant suns through space and time. The atoms in your body were created in stars that lived and died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all were forged in stellar cores and scattered by supernova explosions. You're literally made of stardust, assembled from atoms with a cosmic pedigree spanning billions of years. This connection to the cosmos should inspire wonder. You're not separate from the universe observing it from outside. You're part of it. You're the cosmos examining itself, matter arranged in such complex patterns that it can perceive, think, feel, and understand. That's extraordinary and beautiful and worth celebrating. The knowledge that 200 billion trillion stars exist shouldn't make you feel insignificant. It should expand your sense of possibility. The universe is vast beyond comprehension, filled with more stars than grains of sand on all our beaches. It contains incomprehensible numbers of worlds, unfathomable opportunities for complexity and life and consciousness to emerge. We're living in a universe of extraordinary abundance. It's generous with stars, with planets, with space and time and opportunities for complexity to develop. We're privileged to exist in this moment of cosmic history when stars shine, when galaxies dance, when the universe is young and vibrant and filled with light. And we're privileged to be conscious beings capable of understanding our place in this vast cosmos. We can count stars across the observable universe. We can calculate the age of the cosmos. We can trace our atomic origins to stellar furnaces billions of years ago. We can contemplate our existence and marvel at the magnitude of what we're part of. As we approach the conclusion of this exploration, let's summarize what we've discovered. We began with the challenge of understanding large numbers, building intuition for the difference between millions, billions, and trillions through concrete comparisons. We examined the Milky Way, our home galaxy, containing approximately 200 billion stars, almost all invisible to naked eye observation. We learned about telescopes revolutionizing astronomy by revealing previously hidden cosmic depths. We discussed the observable universe containing approximately 2 trillion galaxies, a number 10 times larger than estimates from just a decade ago. We performed the crucial multiplication. 2 trillion galaxies times an average of 100 billion stars per galaxy equals approximately 200 billion trillion stars in the observable universe. We place this number in context through various comparisons. There are roughly 27 times more stars in the observable universe than grains of sand on all Earth's beaches. Counting them at 1 per second would require over 6 billion trillion years, hundreds of millions of times longer than the universe's current age. Visiting each star for just 1 second would likewise take incomprehensible time. We explored stellar diversity, from tiny red dwarfs that might live for 10 trillion years to massive supergiants that burn brilliantly for only a few million years before exploding as supernovae. We learned that 70 to 75% of all stars are red dwarfs, invisible to the naked eye despite their prevalence. We discovered that stars form from collapsing gas clouds, live by fusing lighter elements into heavier ones, and die as white dwarfs, neutron stars, or black holes depending on their mass. We understood that all heavy elements, including those in our bodies, were forged in stellar cores and scattered by stellar deaths. We acknowledged that most stars probably have planets, suggesting the observable universe contains at least 200 billion trillion worlds, possibly many more. Some fraction of these planets orbit in habitable zones where life might potentially arise. Even if life is extraordinarily rare, the absolute numbers could be staggering. We recognize the uncertainties in our measurements, understanding that the estimate of 200 billion trillion stars might be off by a factor of 2 or 3, but represents remarkable precision given the audacity of measuring the stellar census of the observable universe. We appreciated that this count includes only the observable universe. The total universe might be vastly larger, possibly infinite. Beyond our cosmic horizon lie additional galaxies and stars that we can never observe because their light will never reach us. We explored the cosmic composition, learning that visible stars represent only a fraction of ordinary matter, which itself constitutes only 5% of the universe's total mass energy. Dark matter and dark energy dominate, their natures remaining mysterious despite decades of study. We examined cosmic structure, understanding how those 200 billion trillion stars organize into galaxies, galaxy groups, galaxy clusters, superclusters, and the cosmic web of filaments and voids stretching across observable space. We considered the cosmic future, learning that star formation will eventually cease and the universe will enter a long era dominated by stellar remnants, before even black holes evaporate through Hawking radiation on incomprehensible timescales. We reflected on what this means for humanity and for each of us individually. We're small and brief in cosmic terms, but we're also remarkable. We're conscious matter capable of understanding the cosmos that created us. We're the universe's way of knowing itself. When you step outside tonight and gaze upward, remember what you now understand. Those visible stars are the nearest few thousand of 200 billion trillion. Each point of light represents a massive stellar furnace, probably hosting planets, potentially harboring life, existing somewhere across cosmic distances. The photons entering your eyes have journeyed for years or centuries or millennia to reach you. You're connected through space and time to those distant suns. You're composed of atoms they created. You're part of the same grand cosmic story encompassing all 200 billion trillion stars. This knowledge should fill you with wonder at the magnificent scale of existence. The universe is vast beyond human comprehension. It contains more stars than you could count in 1 trillion lifetimes, more stars than you could visit even with instantaneous travel, more stars than you can meaningfully visualize or conceptualize. Yet we've measured them, we've estimated their numbers, we've grasped something of their natures and their histories. We're small and temporary in cosmic terms, lasting mere decades in a universe that will continue for trillions of years. But we're also extraordinary. We're matter arranged in patterns complex enough to perceive and think and understand. We're the cosmos examining itself, conscious beings capable of contemplating our own existence and our place among the stars. That's remarkable and beautiful and worth celebrating. The fact that conscious beings arose on one small planet, orbiting one ordinary star and figured out how many stars fill the observable universe, speaks to human capability and curiosity and our capacity for wonder. Thank you for joining me on this journey through the cosmos. If this exploration has deepened your sense of wonder and expanded your appreciation for the magnificent universe we inhabit, please consider liking and subscribing. It helps create more content exploring the profound questions about our existence and our place in the cosmos. And may you never look at the night sky quite the same way again. When you see those stars, remember the 200 billion trillion beyond your vision, each one a sun, each one possibly the center of its own system of worlds, each one part of the grand cosmic narrative of matter and energy evolving across billions of years. We counted them, we measured them, We understood our place among them. That's what makes us human. That's what makes this moment in cosmic history special and precious. We're here. We're conscious. We're aware. And we've comprehended something of the magnificent scale of the cosmos we're privileged to inhabit. The night sky awaits you. 200 billion trillion stars shine across the observable universe, each one a testament to the grand processes of stellar birth, evolution, and death that have operated for nearly 14 billion years. We've spent this time together exploring not merely a number, but what that number signifies, how it was derived, and how it connects to our own existence and identity. That's the genuine answer to the question we posed at the beginning: how many stars exist? Not just the count of 200 billion trillion, but the understanding that accompanies it. The recognition that we're part of this cosmos, made of elements created in stars, living on a planet orbiting a star, capable of understanding our position among 200 billion trillion stellar companions. That understanding partially defines our humanity. We can observe the night sky and comprehend what we're witnessing. We can calculate distances to galaxies we'll never visit. We can count stars we'll never individually observe. We can grasp, at least intellectually, the scale of the universe that contains us. This knowledge should fill us with wonder and humility and appreciation. The fact that conscious beings emerged on a small world and determined how many stars fill the cosmos is itself remarkable. We should never lose our sense of awe at what we've discovered and what remains to be discovered. The universe continues revealing its secrets to those patient and curious enough to observe and measure and think deeply about what they find. So when someone asks how many stars there are, you now have a comprehensive answer. Approximately 200 billion trillion in the observable universe, with the possibility of far more beyond our cosmic horizon. More stars than we could ever count individually. More stars than we can meaningfully visualize. More stars than we could visit even in principle, given the vast distances separating them. But each one real. Each one a massive sphere of plasma fusing elements and radiating light into the darkness. Each one part of the grand architecture of galaxies and clusters and filaments comprising the universe's large-scale structure. Each one playing its role in the cosmic story of matter and energy evolving across time. We're here for such a brief moment in cosmic history. The universe existed for billions of years before we arrived, and will continue for trillions of years after we're gone. But right now, in this moment, we exist. We can contemplate these questions. We can marvel at the answers. We can appreciate the extraordinary privilege of being conscious and aware in a vast cosmos. That's the real meaning behind the number, not just 200 billion trillion stars, but what that represents. The cosmic vastness, the incredible diversity of stellar types and evolutionary stages, the chemical enrichment that makes complex chemistry and life possible, the possibility of countless worlds and perhaps countless other forms of life scattered across unfathomable distances. We're small, we're brief, but we're here, we're conscious, and we understand our place among the stars. That's extraordinary and precious and beautiful. That's what makes this moment special. That's what makes us human. Thank you for joining me on this exploration of cosmic scale. If you found value in this journey through the universe, please like and subscribe. It helps me continue creating content that explores the profound questions about our cosmos and our place within it. And remember, when you look up at the stars tonight, you're seeing just the nearest few thousand of 200 billion trillion. The universe is vast beyond measure, filled with more stars than grains of sand on all our beaches. Each one a sun. Each one potentially the center of its own system of worlds. Each one part of the magnificent cosmic story we're privileged to witness and understand. Clear skies. and may you carry with you always a sense of wonder at the magnificent scale of the cosmos we inhabit.